Another use of ion exchange in glass is chemical tempering. In this case, we place a smaller alkali ion with a large ion. Typically we replace sodium by potassium. And this is done in a molten salt bath at a temperature below Tg, which prevents relaxation of the stresses that are induced by essentially forcing a larger ion into the surface. Now, because it is a diffusional process, it is a slow process, and the high surface compressive stresses that are generated by incorporating these large alkali ions in the surface are confined to a few microns in depth. You can go to deeper depths, but there will be more stress relaxation during the process. And there will be compensating interior tensile stresses in all cases. These will be low in all but very thin sections. So schematically what is going on is shown here. So we have our silicate network, our sodium ions effectively in channels, and then potassium ions in the molten salt bath, and over time they exchange by ion exchange as shown schematically here. And the simple model of the stress distribution that arises is shown in this graph. So we have high surface compressive stresses and then compensating tensile stresses to give an overall equilibrium. The surface compressive stresses can be a few hundred megapascals, and on thicker sections the interior tensile stresses will only be a few megapascals. This process has become more common in recent years as it has been applied to the very thin glass that is on the front of mobile devices. The original product for this was Corning Gorilla Glass, which is an alkali aluminosilicate glass which has been designed to give a high case depth during ion exchange. In other words, you can get the ions in a reasonable distance. The glass is in the first place made by what's known as the diffusion overflow process, which avoids touching either side of the glass, and you can get very high toughening stresses with this setup. So this has of course seen wide application in mobile devices in recent years. Oh, that is an example of where ion exchange is useful in glass, whereas the thing that I've spent more time on today is where ion exchange involves essentially attack of glass by water, albeit very slowly, and that was a way of demonstrating how you could deal with the moving boundary problem, but also showed the importance of understanding that diffusion coefficients are actually concentration dependent, and this can have a major effect on the results. And you really do need to understand the relationships between concentration and the diffusion coefficients if you're going to calculate things accurately. Thank you.